Hello, good evening everyone. So am I audible? Can anyone please confirm? Can anyone please confirm? Am I audible? Okay, thank you so much. So good evening everyone. So this is a tutorial session for this course Principles of Modern CDMA MIMO OFDM Wireless Communication course, which is taught by Professor Jagannathan from IIT Kanpur. So this is the first week. So in this we will solve some of the basic questions based on the week 1. Uh, whatever is taught in the week 1, some of the questions based on that, and also we will see some of the theoretical concepts which is taught in the week 1 lecture series. So this class will be from 6 to 8 p.m. So that's why we will cover both questions and theoretical concepts as well. I'm Abhishek Thakur, PMRF scholar from IIT Hyderabad. So this is the week 1 of the tutorial session, and this week it is on Tuesday. From next week it will be on Tuesday and Saturday, and the timing will be mailed through your respective registered mail ID. So we will start now. Around 7 student has joined. So the first question is, like orthogonal frequency division multiplexing OFDM technology is used in which of the following system? So OFDM is basically used in LTE for 4G also, and for 5G NR and 802.11, and so it is used in all of these system. So the correct answer for this question will be all of this. So like in the first week, so basically we will see first the evolution of this wireless technology. So in the 1990s, like 2G was evolved in 1990s. So the technology used in 2G was GSM, CDMA, GPRS, and H. So these were taught in the lecture session. So in 2G, the technology used was GSM, CDMA, GPRS, and this Edge. GPRS and Edge is the advanced version of 2G, so that's why it is also called as 2.5G, because it have more data rate as compared to this. So data rate in GSM is around 10 kb per second. In CDMA also that is same, but in GPRS and Edge it is increased and it was up to 50 kb per second, and in Edge it was up to 200 kb per second. So this was for the 2G. Now coming for the 3G also, like 3G was evolved in around 2000. In that decade it was evolved. So in this, the technology used was WCDMA, UMTS, then CDMA 2000, HSDPA and HSUPA. So the data rate was in 3G was for WCDMA it was around 384 kilobit per second. For CDMA also it was the same one. For HSDPA the data rate is increased, that is from 5 to 30 megabit per second, and for one video it's also 5 to 30 megabit per second. So basically when the wireless communication technology has evolved, the main changes what we can observe in the data rate. So we require higher data rate because the number of devices is increasing day by day. Like the recent technology like Internet of Things, that network multiple devices, and the number of devices on a single network is increasing day by day. So for this we need higher data rate. That's why we need the better wireless communication technology. So now we'll move on to the second question. The second question is the bandwidth of 2G GSM signal is. So for the 2G, the bandwidth was 200 kilohertz. So often option C is the correct answer. We'll move on to the next question. The next question is the waveform employed in an HSDPA system is. So the correct answer for this is code division for multiple access. That is option B. In HSDPA, code division multiple access was used. Now coming to the probability density function for the Gaussian random variable x with 0 mean and variance sigma square is equal to 1. So this Gaussian random variable is of 0 mean and variance 1. So we know how the Gaussian random variable is represented, e to the power of x minus mu. So in this way it is represented. So now here mean is given as 0 and variance is given as 1. So we'll substitute mu is equal to 0 in this equation and sigma square is equal to 1. So our answer will be 1 by 2 pi and sigma square is 1 here and mean is 0. So once mean is 0, we'll put mu is equal to 0 and again sigma square is equal to 1. So the correct answer will be 1 by root 2 pi e to the power of, here I forgot to do the square, e to the power of, here will be minus of x square by 2. So the correct answer from this is option number A. If you have any doubt, you can ask. So we'll move on to the next question. When a Gaussian random process is input to a LTI system, so the output of the LTI system when the input is Gaussian random will be always a Gaussian process only. So option B is the correct answer for the question number 5th. Now coming to the MIMO technology. So MIMO technology is used in wireless system to achieve. So in MIMO, the full form stands for multiple input, multiple output. So there will be multiple number of antenna array in MIMO system, and all antenna arrays together transmit the signal. So definitely the data rate will increase in the MIMO system. So the correct answer is higher data rates. MIMO stands for multiple input and multiple output. So the basically MIMO is used so that the number of antenna will be increased, like the number of antenna array at the transmitter side, it will increase. Once the number of antenna increases, the data rate will also increase, but the complexity will also increase. So that's why, like, once you increase the number of antenna, the computational complexity and the cost of deployment, so these two will increase. That's why we have we have some limitation. So always it should be the optimal number. Let's suppose data rate, the spectral efficiency, that is directly proportional to the data rate. Like if that is directly proportional to the number of antenna. So if number of antenna is k, so that is like directly proportional to k. Let's suppose take a constant alpha, and it is inversely proportional to the complexity and cost. So we have to take the optimal number. So the curve for a spectral efficiency will be like this. So on the x-axis there will be number of antenna, on the y-axis efficiency curve. So efficiency curve depends on data rate by complexity. So once the data, like once the number of antenna increase, this data rate will start increasing and complexity will also increase. But after some point of time, the data rate will not increase significantly, but the complexity will increase very significantly. That's why it will reduce. So that's why we cannot increase number of antenna as like infinitely. So this limitation is done by the limit. It is limited by energy efficiency curve. So basically I have just given some other concept also, but the correct answer for this, MIMO technology is used in wireless system to achieve higher data rate because it have more number of antenna. Now coming to the next question. So the peak downlink data rate of 4G LTE system is approximately of the order, it is around 100 megabit per second. Like in 4G, we have studied 4G uses LTE technology, and WiMAX. LTE stands for long-term evaluation, and WiMAX stands for worldwide interoperability for microwave access. And the data rate is around 100 to 200 megabit per second in this LTE, and in WiMAX it is around 100 megabit per second. Now moving to the next question. And also this video is recorded. Let me check once I have started the recording or not. Yeah, it's recording. So this will be uploaded on YouTube and link will be so the student who have joined late, so for them this video will be recorded and the link will be shared on the NPTEL portal. So you will get access of this video on the YouTube as well. If you have any doubt, you can ask on the YouTube comment box also. Now coming to the next question. Consider a random variable x. The function fx is given as probability of x such that it is less than a value of small x. So it is basically a cumulative distribution function. So cumulative distribution function will start from 0 and end at 1. So the option D is the correct answer, that is cumulative distribution function. It is a CDF function. After these two questions, we will study some of the concepts and then again we will solve 10 questions based on the week 1 lecture series. So coming to consider a possibly complex vector. The vector x hat is given as x1, x2, xn transpose. L2 norm square of this vector is denoted by mod of x1 square plus mod of x2 square plus mod of xn square. So this can be also written as x bar Hermitian, like the vector x Hermitian into the vector x. So this, why we have used this, because Hermitian is used for the complex function also. So here the option C is the correct answer for this question. Now coming to the next question, the digital symbol constellation. Let's suppose this is our imaginary axis and this is our real axis. So the 4 constellation is given, that is 1 plus j. So this is the 1 plus j. Second is 1 minus j. This is also given. The third one is minus 1 plus j. So it is in the second quadrant. And fourth one is minus 1 minus j. So this is the constellation diagram of quadrature phase shift keying, because each phase is differentiated by 90 degree. As you can see, the angle between each phase, if you find the angle between 1 minus j to 1 plus j, you will get 90 degree. And from second to third, you will get 90 degrees. So it is a quadrature phase shift keying. So option B is the correct answer for this question. If you have any doubt, you can ask. Else we will see some of the theoretical concepts from this lecture. Now let's suppose this is the transmitter antenna at the base station. So this is our transmitter at the base station. Now we have, let's suppose this is a mobile system. So this is user 1. So whenever a signal is transmitted from the base station, it can directly reach to the user 1, or it can reflect from the tree, building. Let's suppose there are some tree, building, so it can reflect and then it can go like this. So there are two kind of signals. One is line of sight, another is non line of sight. So for line of sight, the Rician channel is used. For non line of sight, Rayleigh Fedig channel is used. So basically non line of sight is the like the general thing that happens because the environment is very complex and crowded. So we will see about the Rayleigh channel fading in this today lecture. We will study about this. And this all the signal received at the user terminal, that is like superposition of multiple signals. So this is superposition of multiple signal. Like there are multiple signals that coming from the reflections. So this is also known as multi-path propagation environment. So one of the main objective in the wireless system design is to develop a scheme so that it can reduce the fading and ensure reliability of signal reception in the wireless communication system. So now let us analyze this situation. So let us start by considering transmitted passband signal, that is ST. Let's take this is a passband signal ST, which is transmitted across a wireless channel. Such a passband signal can be described analytically as ST is equal to real part of SBT, that is a baseband signal, e to the power of j 2 pi FCT. So here ST is the transmitted passband wireless signal, and SBT is the complex baseband transmitted signal. Representation of the complex baseband representation of ST, that is the passband signal. And here FC is the carrier frequency. Now we will analyze the channel. So the quantity SBT is here the complex baseband representation, and FC is the carrier frequency. Next we need a model for the wireless communication channel. So let us consider like channel with L multipath component. So there is L multipath component in this channel. So each component have two characteristics. First, like there will be some delay. So delay will be tau y, means delay between the each transmitted signal, and there will be some attenuation. So that is given as AI. So from the linear time invariant system, the impulse response of the LTI system, which attenuates the signal by AI and delays by tau y, is given as this HI tau is given as AI del of, this is the unit impulse function, del of tau minus tau I. Okay. Now there is the L multipath component. So our impulse response of the channel H tau will be summation of AI del of tau minus tau I, and here I will go from 0 to L minus 1 because there is L multipath component. Now there will be some component will be non-line of sight, and some will be line of sight, and each such path like I path is characterized by two parameters. First is delay tau I and attenuation AI. Now this is the impulse response of an LTI system. Now the received signal. Now this is the LTI system, and the received signal YT YT, this is YT, is given as the transmitted signal convolution with the channel impulse response. So this is our transmitted signal ST, and HT is the channel impulse response. Now we know the formula of convolution, so we can write YT is equal to integration from minus infinite to infinite. This will be H tau multiplied with S t minus tau d tau. So this is the convolution formula. So now we will use this like H tau whatever is given, what we have found here in the equation 1, we will use equation 1. So by using equation 1, the received signal yt again will be now minus infinite to infinite. H tau is given as summation ai del of t minus tau I. Now we'll take the constant term, like which is not depending on tau, outside of this integration. So after taking, we will get the received signal yt as, so we will get this as I is equal to 0 to L minus 1 ai s of t minus tau I d tau. We know that this del t minus tau I ft, this integration will be f of tau I. Okay. So using this concept we have used, and we have got our received signal as summation of attenuation factor ai into the transmitted signal s with delay tau I. So we'll make it short now. So our s is given by, we'll use this equation also. Let's assume equation a. So now the received signal yt is equal to summation I is equal to 0 to L minus 1 real part of ai s of t minus tau I e to the power of j 2 pi fc tau minus. So here we have used like the equation of this st. So that is given as sbt e to the power j 2 pi fct. So now here t we have transformed tau minus tau I. So with that we will get the equation finally. This is our s of t minus tau I e to the power j 2 pi fc t minus tau I. So this we can write as e to the power minus j 2 pi fc tau I will bring inside, and e to the power j 2 pi fc t. So this is our carrier signal with carrier frequency fc. This is the carrier frequency, and this is our complex baseband signal. So this we can finally write as,
Good evening, sir. Can you hear my voice? Please
so
respond me, sir.
this is our complex coefficient, channel coefficient.
Hello.
So finally, yt can be written as channel coefficient with multiplied with the signal component st. And here our h is equal to what we have already derived, ai e to the power of minus j 2 pi fc tau y, and I is equal to 0 to l minus 1. So this h depends on the attenuation factor ai and the delay tau y. So sometimes when signals are coming like non line of sight, so it can be a constructive or destructive interference. Like the interference can be constructive or destructive. So now we'll solve some question. Then again we'll come to the theoretical part. So in this question, it is asking which of the following is not a 3G or 3.5G wireless standard. We all know that these three, HSDPA, HSUPA, and WCDMA, is the 3G or 3.5G wireless standard. GSM is the correct answer. This is not a 3G or 3.5G. It's for 2G standard. Okay. So option A is correct. Now the option B, the real and imaginary part of standard wireless channel coefficient described in lectures are assumed to be described as. So this will be Gaussian random variable. We will solve this question. So we will continue this derivation so that we can solve the question number 2 also and the other question as well. Sorry for the disturbance. I got some call. So now the fading channel coefficient, what we have described here, this is a summation of like it depends on the attenuation factor ai and the delay tau I. So if we write h is equal to x plus jy, So here x we will consider as summation of I is equal to 0 to L minus 1 AI cos 2 pi fc tau I. Okay, and y will be our sine term, so that will be 0 to L minus 1 AI sine of 2 pi fc tau I. Because here this j is there, so when you like break this complex term into real and imaginary part, so this is our real part and this is our imaginary part. So just give me a time, I've got some call. Hello. Sorry for the disturbance. So now let's assume x and y to be a Gaussian distribution. So for the Gaussian distribution, let's suppose x is Gaussian distribution with mean mu and variance sigma square. So this can be written as 1 by 2 pi sigma square e to the power of minus, we can write like this. And the Gaussian distribution function is and let's suppose the mean is 0 and mu is equal to 0 and the variance is half, then our fx will be 1 by root under uh, 2 pi into half e to the power of minus x minus mu square by 2 sigma square. So this will become 1 by root pi e to the power of minus, mean is 0 and sigma square will be half, so it will be e to the power of minus x square. So for similarly y is, let's suppose, 0 mean and half variance Gaussian random variable, then fy will be 1 by root under pi of e to the power of minus y square. So assuming x, y are independent random variable, we can write the joint distribution as fx x into fy y. So this is the joint distribution. So this will be written as 1 by root pi e to the power of minus x square into 1 by root pi e to the power of minus y square. So this will become 1 by pi e to the power of minus x square plus y square. So the magnitude will be, and our channel was x plus jy. So this can be written as a e to the power of j phi. So here a is the magnitude, so that is equal to x square plus y square, and the phase is tan inverse y by x. So we can now we can find like the x and like channel was the summation of x plus jy, so that can be represented as a e to the power of j phi. So now these two are in the different variables. So in this what we can do, we can find f of a phi is equal to 1 by pi e to the power minus x square plus y square Jacobian of xy. So e to the power of x square plus y square will be a square, and we will find Jacobian of xy. So we will get del x by del a, del y by del a, del x by del phi, and del y by del phi. And here our x is here we can take x is equal to a cos phi and y is equal to a sin phi. So after this we will get as cos phi sin phi minus a sin phi and a cos phi. So when you find, you will get a cos square phi plus a sin square phi. So the final answer will be a only. This is equal to 1 by a by pi e to the power minus x square plus y square. And x square plus y square is a square. So here we can directly write a square. Now when you find fa of a, we will get 2a e to the power of minus a square as described in the lecture. You can do the calculation. Fa of a is equal to integration over minus pi to pi fa phi a phi d phi. And same way, when you find f of phi, you will get it will be a simple pi value like 1 by 2 pi. So when we multiply, you can find this by simple derivation how it is described in the lecture series. So fa phi a comma phi, that is equal to fa of a into f phi of phi. So this is the independent random variable. The graph for this will be like this. So this is the Rayleigh fading channel, and this is constant over minus pi to pi, and the value will be 1 by 2 pi. So this is our joint density, and this is the product of marginal density. So in this question, the real and imaginary part of the standard wireless channel coefficient is described in the lecture as here we have taken The real and imaginary part like fxx and ffy is the Gaussian function. So the correct answer is for this question is Gaussian random variable. Now coming to the next question, the phenomenon in which the channel coefficient is constantly changing is termed as. So for this, the answer will be fading. The correct answer is option D, that is fading. Because channel concept coefficient is constantly changing. This term is known as fading, and it depends on attenuation AI and delay tau I. Coming to the next question, the probability density function of an exponential random variable x defined for x is greater than equal to 0 with mean 2 is. So we know the probability density function for the exponential random variable is lambda e to the power of minus lambda x. This is for the exponential random variable. Whatever we studied before was the Gaussian random variable. So here lambda mu is equal to 1 by lambda. So in this question mean is given as 2. So lambda is equal to 1 by 2. So our fxx will be 1 by 2 e to the power of minus half of x. So the correct answer for this question is option number B. Now the probability density function Fa of the amplitude A of the Rayleigh Fading channel coefficient with average gain unity is. So we have already studied that is 2a e to the power of minus a squared. So for this the option D is the correct answer for this question. Now which of the following is the 4G wireless standard? For 4G we all know LTE is the 4G wireless standard. So option B is the correct answer here. Now the distribution of phase of the Rayleigh Fading channel coefficient is. So the phase is defined 1 by 2 pi, that is from minus pi to pi, or you can take from 0 to 2 pi. This will be more appropriate. The value will be 1 by 2 pi. So this is the uniform random variable. So option A is the correct answer for this question. Now what is the data rate of HSDPA? We have already studied. So the data rate of HSDPA is a 5 to 30 megabit per second. This is a 3G wireless standard. Now the acronyms WCDMA stands for. So that is wideband code division multiple access. So option A is the correct answer for this question. Now coming to the next question. This is a numerical question. So in this question it is asking the probability that the attenuation of the Rayleigh Fading channel is worse than 40 dB is approximately. So we know it can be calculated as 10 log 10. Attenuation is given as A. It should be less than minus 40 dB. So it is worse than 40 dB. So it will be less than minus 40 dB. So now this can be written as less than minus 4, and a square sorry, so this can be written as a is less than 10 to the power of minus 2. So the answer will be like 0.01. And it in this question it is asking the probability that attenuation. So probability from 0 to 10 to the power of minus 2, the attenuation is given as 2a e to the power minus a square dA. So this we have to find. So for this, let's assume a square is equal to t, 2a dA is equal to dt. So now substitute this value 0, and this will be a square. T is equal to a square, so 10 to the power minus 4, and 2a dA is equal to dt. So it will be e to the power of minus t dt. We can write as minus e to the power of minus t. So now this will be minus e to the power minus t, and here we'll substitute the value. First t is equal to 0, so it will be 1 plus e to the power of minus 10 to the power of 4 minus 4. So this is equal to e to the power minus 10 to the power of minus 4 minus 1. So when you find this, we'll get approximately as 0.0001. So option A is the correct answer for this question. We'll also solve some other questions. There was a question in the lecture series itself. At SNR is equal to 10 dB, what is the bit error rate for our AWGN communication system with BPSK modulation? So before moving to the question, we'll see for BPSK modulation what will be the bit error rate. Let's suppose x is equal to 1 is denoted as minus root over p, and x is equal to 0 is denoted as root over plus root over p, and the received signal y is equal to x plus n. So let's suppose bit 1 is transmitted. So the received signal will be minus root p plus n, and bit error will occur if y is greater than 0. Like this means y is greater than 0 means bit 0 is received. So here you can see 1 is transmitted and 0 is received. So 1 is transmitted and 0 is received. So there is an error. So error has occurred. So now when will be y greater than 0? This means this term is greater than 0 because this is equal to y. This implies that when the noise is greater than root p, then the error will occur. This means noise is very dominant. So probability of error such that probability n is greater than root over p is equal to 1 by root under 2 pi e to the power of minus t square by 2 dt. So this can be written as probability of E is, this is the quotient function of root under p by sigma square. So this is p by sigma square is signal is to noise ratio. P is the signal ratio and is equal to S and R. So P is signal ratio and sigma square is the noise ratio. So now coming to the question. In this question SNR is given as 10 dB. So now convert the SNR in normal units, not in dB. We will get SNR is equal to 10 to the power of 1. So this is equal to 10. Okay. Now probability of error is Q of root of SNR. So that is equal to Q of root of 10. So probability of error that is equal to, when you calculate this value, we will get 7.8 into 10 to the power of minus 4. We can solve some other example. So today we will bind up in 10 minutes. We'll take 10 more minutes because already we have finished most of the questions. So this quiescent function q of x is given as like it is always less than half e to the power of minus half of x square. Okay, so we can approximate it as half e to the power of minus half x square. So whenever, let's suppose, the bit error rate that is given as quiescent function of square root of SNR, so this can be written as half e to the power of, here x is root over SNR, so x square will be SNR. So x square will be SNR. So also we can use this equation for the SNR. What is SNR dB required for bit error rate equal to 10 to the power of minus 6, and it is given BPSK over the additive wise Gaussian noise channel. So in this we know that bit error rate is given as half e to the power of minus half of SNR, and this is given as 10 to the power of minus 6. So e to the power of minus half SNR, that is equal to 2 into 10 to the power of minus 6. So SNR is equal to minus 2 ln 2 into 10 to the power of minus 6. So when we calculate this, the answer we will get is 26.24. Now convert this SNR into dB, that is equal to 10 log 10, 26.24. So the answer will be 14.19 dB. We will solve one more question. This time we will solve based on the delay. Consider a wireless signal. This is the last question for today. Wireless signal with carrier frequency 850 megahertz. So this is the carrier frequency given. Now, which is transmitted over a wireless channel that results L is equal to 4 multipath components at a delay of 201, 513, 819 and 1223 nanosecond, and corresponding to receive signal amplitudes of 1, 0.6, 0.3 and 0.2. Now derive the expression for the received. Now we have to find two things. Derive the expression for first received baseband signal YBT if the transmitted signal is SBT. Second, derive the corresponding received signal with the narrowband assumptions. So here in this question you can see the delay is given for all the four multipath components. So this is tau 1, tau 2, tau 3 and tau 4. And the signal amplitude is given that is 1, 0 0.6, 0 0.3 and 0 0.2. So now we'll find this question, solve this question. So we need to compute hi, that is equal to ai e to the power of minus j 2 pi fc tau I. So our a naught is equal to 1, tau naught is equal to 201 nanosecond. A1 is equal to 0.6 and tau 1 is equal to 513 nanoseconds. A2 is equal to 0.3 and tau 2 is equal to 819 nanosecond. A3 is equal to 0.2 and tau 3 is equal to 1223 nanosecond. So h naught is equal to a naught e to the power of minus j 2 pi fc tau naught. When you substitute this value, it will be 1 e to the power of minus j 2 pi. Fc is given as 850 megahertz. So 850 into 10 to the power of 6 and tau naught is 201 nanosecond. So when you solve this you will get as 0.59 plus j of 0.81. So similarly you can solve by substituting all the value of a naught and ai and tau I. So finally you will get the final answer you will get yb of t is equal to 0.59 plus j of 0.81 sbt plus 0.57 minus j of 0.19 sbt plus minus 0.19 plus j of 0.06 sbt. Sorry, here will be delay also. We have to include the delay factor also. The first signal will be without delay. The second signal will be delay with 100, 201 nanosecond. So here we have to do t minus 201 into 10 to the power of minus 9 and then plus 0.18 minus j of 0.24 into sb t minus 513 nanosecond plus minus 0.19 plus j into 0.06 sb t minus 1223 nanosecond. So this was the part 1. Now part 2, yt is equal to summation of I is equal to 0 to 3 ai e to the power minus j 2 pi fc tau I sbt. So this will be 1.14 plus j is 0.44. When you calculate this, you will get this answer. So ybt is equal to h of sbt. So when we are assuming the narrow band assumption, then we are not assuming this delay part. So we can directly add the so this delay is ignored here. So we can directly add the real and imaginary part. So we will close the lecture here only today, and I will share this slide, and also this video is recorded, and it will be uploaded on the uh, YouTube, and the link will be shared there. So thank you everyone for attending. So we can close the lecture here. We will again meet next Tuesday at same time at 6 to 8.
Thank you, sir.
Thank you, sir.